Hello, we are starting the book Electronics Fundamentals by Floyd Butler 8th edition. I'm just on just scrolling through chapter 1, see if there is something important to take to with us, and then we will go to chapter 2. I will try to avoid the absolute basics most much as possible. Although I like basics, but I cannot continue always using time on the basics. I will never get any further. Okay, we have this. I want to read a little bit electric shock. It's a little interesting to be like reminded of. Electrical shock. Current through your body. Not the voltage is the cause of electrical shock. Of course, it takes voltage across resistance to produce current. When a point on your body comes in contact with a voltage and another point comes in contact with a different voltage or with the ground, such as metal chases, there will be current through your body from one point to the other. The path of the current depends on the points across which the voltage occurs. The severity of the resulting electrical shock depends on the amount of voltage and the path that the current takes through the body. The current path through the body determines which tissue and organs will be affected. The current path can be placed into three groups which are referred to as touch potential, step potential, and touch step potential. Ja, sånn se her. So that is interesting. I am actually wondering about this. I never like speak about it about anyone, but I'm just thinking, will if you get electric shock somewhere, I'm thinking, will it go through your entire body, roam around your body, or will it just go the fastest way through, and then the other parts of the body will not be affected at all? That's what I'm wondering, because. Yes, because everything is touching each other, in the body. So I guess it will roam around, but I learn now that it will not. It will go the fastest way. I see. The amount of current is dependent on voltage and resistance. The human body has resistance that depends on many factors, which include body mass, skin moisture, points of contact of the body with the voltage potential. And this table shows the values of current in milliamperes. Okay, yeah. Physical effects of electrical current. It may vary on body mass. Okay, yeah, but this is truly interesting. I am totally going to note myself this. So here, as milliampere, it sounds very little, but okay. Oh, 4,000. Okay, 235. That is, then it starts. Okay, well, it sounds like it means that from 235 milliampere it can be fatal. But then I understand that anything below that, it's not fatal. But did they make that limit exactly there? Because yeah. Usually fatal for duration 5 seconds or more. Okay. Heart paralysis. Okay, alright. Body resistance. Resistance of the human body is typically between 10 kilo ohm. Is it ohm? I think so. And 50 kilo ohm. Or 50,000 ohm. And depends on the 2 points between which is measured. The moisture of the skin also affects the resistance between 2 points. The resistance determines the amount of voltage required to produce each of the effects listed in Table 4. For example, if you have a resistance of 10,000 ohm between two given points in your body, 90 volts across those points will produce enough current to cause painful shock. Utility voltages. We tend to take utility voltages for granted, but they can be and have been lethal. It is best to be careful around any source of voltage. Even low voltages can present a serious burn hazard. As a general rule, you should avoid working on an energized circuit and check that the power is off with a known good meter. Most work in educational labs uses low voltages, but you should still avoid touching an energized circuit. If you are working on a circuit that is connected to utility voltages, the service should be disconnected. A notice should be placed on the equipment or placed where the service is disconnected, and a padlock should be used to prevent someone from accidentally turning the power on. This procedure is called lockout tagout and is widely used in industry. There are specific OSHA and industry standards for lockout tagout. Most laboratory equipment is connected to the utility line, and in North America this is 120 volt RMS. A faulty piece of equipment can cause the hot lead to inadvertently become exposed. You should inspect cords for exposed wires and check equipment for missing covers or other potential safety problems. The single-phase utility lines in homes and electrical laboratories use three insulated wires that are referred to as the hot black-red wire or neutral white wire. The hot and the neutral wires will have current, but the green safety line should never have current in normal operation. The safety wire is connected to the metal exterior of the encased equipment and is also connected to a conduit and the metal boxes for housing receptacles. Figure 2 shows the location of the conductors on a standard receptacle. Notice on the receptacle that the neutral lead is larger than the hot lead. The safety ground should be connected to the neutral at the service panel. The metal chassis of an equipment or appliance is also connected to the ground. In the event that the hot wire is accidentally in contact with ground, the resulting high current should trip the circuit breaker or open a fuse to remove the hazard. However, a broken or missing ground lead may not have high current until it's contacted by a person. This danger is one obvious reason for ensuring that line cords have been altered by removing the ground pin. Many circuits are further protected with a special device called a ground fault circuit interrupter. If a fault occurs in a GFCI circuit, a sensor detects that the current in the hot line and the neutral line are not equal as they should be and trips the circuit breaker. The GFCI breaker is very fast. It's very fast acting and trip faster than a breaker on the main panel. GFCI breakers are required in areas where the shock hazard exists, such as where there is water or moisture. Pools, bathrooms, kitchens, basement and garages should all have GFCI outlets. Figure 3 shows a ground fault receptacle with reset and test buttons. When the test button is pressed, the circuit should immediately open. The reset button restores power. Safety precautions. There are many practical things that you should do when you work with electrical and electronic equipment. Some important precautions are listed here. Avoid contact with any voltage source. Should I read this or should I just... Okay, we have some questions there. Section 5, checkup. What causes physical pain and or damage to the body when electrical contact is made? The current going through the body. And that is produced by voltage. Yes, and it's reduced by resistor. It's OK to wear a ring and working on electrical circuit. Yeah, I wonder about that. Remove rings when you work on circuits. Okay. Great. Standing on a wet floor presents no safety hazard when working with it. That is false. It is a safety hazard if you have water involved. A circuit can be rewired without removing power if you're careful. I think that's false. You should always remove the power. Electrical shock can be extremely painful or fatal. True, yes. What does GFCI stand for? What was a GFCI? Here it is. GFCI is ground fault circuit interrupter. Ground fault circuit interrupter. I don't know, I always remember to. Then okay, here's some more quiz. The number 3,300 is written as 3.3 times the 3 power of 10 in both scientific and engineering notation. Yes, I guess so. A negative number that is expressed in scientific notation will always have a negative exponent. Negative number, no. A negative exponent is if it's a small number with comma. When you multiply two numbers written in scientific notation, the exponents needs to be the same. Do they? Not. I think something needs to be the same. Well, I investigate that. I think that the exponents I think the main number must be the same. Not the exponent doesn't need to be the same, because when you multiply these exponents, you will only have a yeah. Same as 4,700. 1, 2, 3. This is the same as 0.056. Yes. This one. Yeah, this one, but I think they like to do this. This one. Ja, ARC 20 million ohms can be expressed as 20. It must be the C 20 ohm. Hertz is due to frequency. Ohm. Volt. Ampere. Okay. So what now? Voltage, current, and resistance. Okay, this here will be about atoms, electrical charge, voltage, current, resistance, electric circuit, basic circuit measurement, application assignment, putting your knowledge to work. Okay, you will be able to describe the basic structure of an atom, explain concepts of electrical charge, define voltage and discuss its characteristics, define current and discuss its characteristics, and resistance. Describe a basic electric circuit, make a basic circuit measurement. I assume you wanted to have an interactive quiz board as part of a science fair display. The quiz bar will use a rotary switch to select one of 4 options that represent battery types. Each position of the switch lights a light. The person viewing the display selects the matching answer by pressing a push button next to one of the 4 possible answers. If the correct push button is pressed correct, light is illuminated, otherwise nothing happens. The overall brightness of the light is controlled by a single rheostat. Introduction. 3 basic electrical quantities presented in this chapter are voltage, current, and resistance. No matter what type of electrical or electronic equipment you may work with, these quantities will always be of primary importance. This is true for DC and AC circuits, but our focus will be DC circuits because of its importance in electrical application. An AC circuit may be used occasionally to illustrate a particular concept. However, in these special cases, the analysis and calculations are the same as for an equivalent DC circuit. To help you understand voltage, current, and resistance, the basic structure of the atom is discussed and the concept of charge is introduced. The basic electric circuit is studied along with techniques for measuring voltage, current, and resistance. And then atoms. Well, this can be that. Atoms. All matter is made of atoms, and all atoms consist of electrons, protons, and neutrons. The configuration of certain electrons in an atom is the key factor in determining how well a conductive or semiconductive material conducts electric current. An atom is the smallest particle of an element that retains the characteristic of that element. Each of the known 110 elements has atoms that are different from the atoms of all other elements. Gives each element a unique atomic structure. According to the classic Bohr model, an atom is visualized as having a planetary type of structure that consists of a central nucleus around by orbiting electrons, as illustrated in figure 1. The nucleus consists of positively charged particles called protons and uncharged particles called neutrons. The basic particles of negative charge are called electrons. Electrons orbit the nucleus. Each type of atom has a certain number of protons and distinguish it from the atoms of all other elements. For example, the simplest atom is that of hydrogen, which has one proton and one electron. As pictured in the figure. As another example, the helium atom, shown in the figure 2b, has 2 protons and 2 neutrons in nucleus and 2 electrons orbiting the nucleus. This is the Bohr model of an atom showing electrons in circular orbits around the nucleus. The tails on the electrons indicate that they are moving. That they are moving around. Right. Here you have a hydrogen atom. And then we have helium. These are the simplest atoms, hydrogen and helium. Atomic number. All elements are arranged in periodic table of the elements according to the atomic number. The atomic number equals the number of protons in the nucleus. For example, hydrogen has an atomic number of 1 and helium has an atomic number of 2. In a normal or neutral state, all atoms of a given element have the same number of electrons and protons. The positive charges cancel negative charges, and the atom has a net charge of 0, making it electrically balanced. Electron shells and orbits. Electrons orbit the nucleus of an atom at certain distances from the nucleus. Electrons near the nucleus have less energy than those in more distant orbits. Is it known that only discrete values of electron energies exist within atomic structures? Therefore, electrons must orbit only at discrete distances from the nucleus. Energy levels. Each discrete distance from the nucleus corresponds to a certain energy level. In an atom, the orbits are grouped into energy bands known as shells. A given atom has a fixed number of shells. Each shell has a fixed maximum number of electrons at permissible energy levels. The shells are designated 1, 2, 3 and so on, with 1 being closest to the nucleus. This energy band concept is illustrated in figure 3, which has 2 energy levels. Additional shells may exist in other types of atoms depending on the elements. The number of electrons in each shell follows a predictable pattern according to the formula 2n, where n is the number of the shell. The first shell of any atom, n equals 1, can have up to 2 electrons. The second shell is up to 8 electrons, and the third shell up to 18 electrons, and the fourth shell up to 32 electrons. In many elements, electrons start filling the fourth shell after 8 electrons are in the third shell. Valence electrons. Electrons that are in orbits farther from the nucleus have a higher energy and are less tightly bound to the atom than those closer to the nucleus. This is because the force of attraction between positively charged nucleus and negatively charged electrons decreases with increasing distance from the nucleus. Electrons with the highest energy levels exist in the outermost shell of an atom and are relatively loosely bound to the atom. Its outermost shell is known as the valence shell, and the electrons in this shell are called valence electrons. These valence electrons contribute to chemical reactions and bonding within the structure of material, and they determine material's electrical properties. Valence electrons. The electrons that exist in the element's outer shell, they are loosely bound to the element and contribute to chemical reactions. They also determine a material's electrical properties. Free electrons and ions. If an electron absorbs a photon of sufficient energy, it escapes from the atom and becomes a free electron. Any time an atom or group of atoms is left with a net charge, it is called an ion. When an electron escapes from the neutral hydrogen atom designated H, the atom is left with a net positive charge and becomes a positive ion. In other cases, an atom or group of atoms can acquire an electron, in which case it is called a negative ion. Copper is the most commonly used metal in electrical applications. The copper atom has 29 electrons that orbit the nucleus in the 4 shells, as shown in figure 4. Notice that the fourth or outermost shell, the valence shell, has only one valence electron. The inner shells are called the core, and the valence electron is the outer shell of the copper atom gains sufficient thermal energy. It can break away from the parent atom and become a free electron. In a piece of copper at room temperature, a sea of these free electrons is present. These electrons are bound to a given atom but are free to move in the copper material. Free electrons make copper an excellent conductor and make electrical current possible. Categories of materials. Three categories of materials are used in electronics: conductors, semiconductors, and insulators. Conductors are materials that readily allow current. They have large numbers of free electrons and are characterized by 1 to 3 valence electrons in their structure. The most metals are good conductors. Silver is the best conductor and copper is next. Copper is the most widely used conducting material because it's less expensive than silver. Copper wire is commonly used as a conductor in electric circuits. Semiconductors are classed below the conductors in the ability to carry current because they have few free electrons than conductors. Semiconductors have 4 valence electrons in their atomic structures. However, because of their unique characteristics, certain semiconductors materials are the basis for electronic devices such as the diode, transistor, and integrated circuit. And then they are classed below conductors in the ability to transfer current because they have fewer free electrons than conductors. Semiconductors have 4 valence electrons in their structure. Certain materials are basis for electronic devices like diode, transistor, and integrated circuit. Typical materials is silicon and germanium. Insulators. Insulator are non-metallic materials that are poor conductors of electric circuit. They are used to prevent current where it's not wanted. Insulators have no free electrons in their structure. Their valence electrons are bound to the nucleus and are not considered free. Although non-metal elements are generally considered to be insulators. Most practical insulators used in electrical and electronic applications are compounds such as glass, porcelain, Teflon, polyethylene, to name a few of them. Non-metallic materials which have poor ability to transfer current. They are actually used to prevent current where it is not wanted, and to protect a circuit. These materials have no free electrons in their structure. The valence electrons are bound to the nucleus and is not considered to be free. some of the most typical materials as insulators is glass, porcelain, Teflon, and polyethylene. Okay, we have some questions and answers. I'm gonna have that up, and then we will write these answers. You see. What is the basic particle of a negative charge? Electron. Atom. Is material. Atom consists of neutrons, protons, and electrons. Neutrons and protons are in the core of the atom, and the electrons are moving around in the shells around the core. Atomic number is the number of either number is also called the proton number, and then it's the number of protons in the atom. No, they don't. The point is that they are different. A free electron is the electrons which exist in the outer shell of the atom. They are loosely bound to the nucleus, and are free to react with other atoms. The shell in the atomic structure is where the electrons are. Two conductive materials, silver and copper. As you know, an electron is the smallest particle that exhibits negative electrical charge. When an excess of electrons exists in a material, there is a net negative electrical charge. When a deficiency of electrons exists, there is a net positive electrical charge. When you complete this section, you should be able to know a little bit of electrons. I'll explain concept of electrical charge. Name unit of a charge, name types of charge, describe the forces between charges, determine amount of charge on a given number of electrons. The charge of an electron that are equal in magnitude and opposite in sign. Electrical charge is an electrical property of matter that exists because of an excess of deficiency of electrons. Charge is symbolized by Q. Static electricity is the presence of a net positive negative charge in material. Everyone has experienced the effects of static electricity from time to time. For example, when attempting to touch a metal surface or another person, or when the clothes in a dryer cling together. Materials with charges of opposite polarity are attracted to each other. Materials with charges of the same polarity are repelled as indicated symbolically in Figure 5. A force acts between charges as evidenced by an attraction or repulsion. This force, called an electric field, consists of invisible lines of force as represented in Figure 6. Uncharged, there is no force. If they are charged but opposite, they attract each other. Same positive charge, they will avoid each other. And the same will this same. Electric field. Coulomb's law. A force F exists between 2 point source charges that is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the charges. One coulomb is a total charge possessed by 6.25 times 10 to the power of 10 electrons. A single electron has a charge of So if you have that many electrons, then you will get one column. Charge Q is one column. Positive and negative charge. Consider a neutral atom. That is, one that has the same number of electrons and protons and thus has no net charge. As you know, when a valence electron is pulled away from the atom by the application of energy, the atom is left with a net positive charge, more protons than electrons, and becomes a positive ion. A positive ion is defined as an atom or group of atoms with a net positive charge. The amount of energy to free a valence electron is related to the number of electrons in the outer shell. An atom can have up to 8 valence electrons. The more complete the outer shell, the more stable the atom, and thus the more energy is required to remove an electron. Figure 7 illustrates the creation of a positive ion and a negative ion when a hydrogen atom gives up its single valence electron to a chlorine atom from a gaseous hydrogen chloride. When the gaseous is dissolved in water, hydrochloric acid is formed. For example, how many columns of charge do 93.8 plus 1060 electrons per cell? That we will find out. We will write in the formula. We are remembering this formula. Q equals number of electrons (6.25 times 1018 And then we'll write. Okay, and then we will have and then we will have calculator to answer. Huh? Okay, I'll try again. 93.8 times 10, 16, divide 6.25 times 10, 18. And that would be 0.0. So that is 0.15008 columns of charge. Okay, do I have okay. Okay, to do that, we have to then we must write the then we must just rewrite this formula. We must write 3c, and then we will multiply with 6.25 times 10, 18, and then we will get the number of electrons, and then we will get 3 times 6.25 times 10 divided 18, and then we will get so 1.875 times 10, 19. That is the and that will be the answer. And then we have the question answer for this. What is the symbol used for charge? That is Cl Q, I guess that's C for C, the column, or a Q, like that. Okay, Q is for charge. C, unit of charge is Coulomb equals C. Okay. Negative charge and positive charge. Okay, so how much charge is that? 10 times 10, 12, and divide on 6.25 times 10 in 18, and then 1.6 times 10 negative 6 charge. Okay, we will continue the next number 3 voltage a little later. Oh yeah, we are now on voltage. Let's see. Let's continue with this. 3 voltage. As you have learned, the force of attraction exists between a positive and negative charge. A certain amount of energy must be exerted in the form of work to overcome the force and move the charges a given distance apart. All opposite charges possess a certain potential energy because of the separation between them. The difference in potential energy of the charges is the potential difference or voltage. Voltage is the driving force in electric circuits and is what establishes current. After completing this section, you should be able to define voltage and discuss its characteristics. State formula of voltage. Name and define unit of voltage. Describe basic sources of voltage. Voltage is defined as energy per unit of charge and is expressed as where V is voltage in volts, W is energy in joules, and Q is the charge in coulombs. As a simple analogy, you can think of voltage as corresponding to the pressure difference created by a pump that causes water to flow through a pipe in a closed water system. Volt, the unit of voltage. The unit of voltage is the volt, symbolized by V. 1 volt is the potential difference voltage between 2 points, and 1 joule of energy is used to move 1 coulomb of charge from one point to other. In 50 G of energy are required to move 10 coulomb of charge. What is the voltage? Skal vi se, da gjør vi bare sånn da. Vi det er nok lite effektivt her, så jeg kanskje vil lære meg. Så 5 til på 10. Kan vi lire i OD da? 5. 5 V. How much energy is required to move 50 C from one point in circuit to another when the voltage between 2 points is 12 volt? Ja, skal vi se da. Vi har byttet ut 12. Og den er jo dobbelt det. Og den er dobbelt V. Da dobbelt V er lik 12 ganger 50, det blir 600. Det blir 600, sant? Vi kjører. Symbol for DC voltage sources. That's sånn, that looks like that. The DC voltage sources. A voltage source provides electrical energy or electromotive force, EMF. I will write that down. EMF equals electromotive force, more commonly known as voltage. Okay. Voltage. Okay, voltage. Fine, then I know that. Voltage is produced by means of chemical energy, light energy and magnetic energy combined with mechanical motion. The idea of voltage source can provide a constant voltage for any current required by a circuit. The idea of voltage source does not exist but can be closely approximated in practice. We will assume ideal unless otherwise specified. Voltage sources can be either DC or AC. A common symbol for a DC voltage source is shown in the figure here. A graph showing current versus voltage for an ideal DC voltage source is shown in the figure below. As you can see, the voltage is constant for any current from the source. For a practical, non-ideal voltage source connected in a circuit, the voltage decreases slightly as the current increases, as shown by the dashed line. Current is also drawn from a voltage source when a load such as resistance is connected to it. Okay, that's interesting. Okay, so we said the voltage constant for our ideal, right? For practical, like when you do it in practical in real life, like which is non-ideal, the voltage surge decreases slightly as the current increases. That's interesting. I'll read what stands here. History. Alessandro Volta, 1745 to 1827. Volta, an Italian, invented device to generate static electricity, and he discovered methane gas. Volta investigated reactions between dissimilar methods and developed the first battery in 1800. Electrical potential, more commonly known as voltage, and the unit of voltage, the volt, are named in his honor. Types of DC voltage sources. Batteries. A battery is a type of voltage source that is composed of one or more cells that convert chemical energy directly into electrical energy. As you know, work per charge is the basic unit for voltage, and the battery adds energy to each unit of charge. It is something of a misnomer to talk about charging a battery, because a battery does not store charge, but rather stores chemical potential energy. All batteries use a specific type of chemical reaction called an oxidation-reduction reaction. In this type of reaction, electrons are transferred from one reactant to the other. If the chemicals used in the reaction are separated, it is possible to cause the electrons to travel in the external circuit, creating current. As long as there is an external path for the electrons, the reaction can proceed, and stored chemical energy is converted to electrical current. If the path is broken, the reaction stops and the battery is said to be in equilibrium. In a battery, the terminal that supplies electrons has a surplus of electrons and is the negative electrode or anode. The electrode that acquires electrons has a positive potential and is the cathode. The figure shows a non-rechargeable single-cell copper zinc battery that we will use for illustration of battery operation. The copper zinc cell is simple to construct and illustrates concept to all non-rechargeable batteries. A zinc electrode and a copper electrode are immersed in solutions of zinc sulfate and copper sulfate, which are separated by a salt bridge that prevents the Cu2+ ion from reacting directly with the zinc metal. The zinc metal electrode supplies Zn2+ ions to the solutions and electrons to the external circuit. So this electrode is constantly eaten away as the reaction proceeds. The salt bridge allows ions to pass through it to maintain charge balance in the cell. There are no free electrons in the solution, so an external path for electrons is provided through an ammeter or other load. On the cathode side, the electrons that were given up by the zinc copper electrode were given up by the zinc combined with copper ions from the solution to form copper metal, which deposits on the copper electrode. The chemical reactions occur at the electrode. Different types of batteries have different reactions, but all involve transfer of electrons in the external circuit and migration of ions internally as the battery discharges. A single cell will have certain fixed voltage. In the copper zinc cell, the voltage is about 1 volt. In a lead acid cell, the kind used in the car batteries, a potential difference of about 2.1 volt is between the anode and the cathode. A typical car battery has 6 such cells connected in series. The voltage of any cell depends on the cell chemistry. Nickel-cadmium cells are about 1.2 volt, and lithium cells can be as high as almost 4 volt, depending on the second reactant. Safety note: lead acid batteries can be dangerous because sulfuric acid is highly corrosive and battery gases are explosive. The acid in battery can cause serious eye damage if it contacts the eye and cause skin burns or destroy clothing. You should always wear proper eye protection when working on or around batteries, and wash well after handling batteries. And taking a battery out of service, disconnect the ground and first. This prevents current and avoids a potential spark when the positive lead is disconnected. Copper zinc battery. The reaction can only occur if an external path is provided for the electrons. As the reaction proceeds, the zinc anode is eaten away and the copper 2+ ions combine with electrons to form copper metal on the cathode. Cell chemistry also determines the shelf life and discharge characteristics for a battery. For example, a lithium MnO battery typically has 5 times the shelf life as a comparable carbon zinc battery. Although the voltage of a battery cell is fixed by its chemistry, the capacity is variable and depends on the quantity of materials in the cell. Essentially, the capacity of a cell is the number of electrons that can be obtained from it and is measured by the amount of current that can be supplied over time. Batteries normally consist of multiple cells that are electrically connected together internally. the way that the cells are connected and the type of cells determine the voltage and current capacity of the battery. If the positive electrode of one cell is connected to the negative electrode of the next, and so on. As illustrated in the figure, the battery voltage is the sum of the individual cell voltages. This is called series connection. To increase battery current capacity, the positive electrodes of several cells are connected together and all the negative electrodes are connected together. As illustrated in figure 11b, this is called a parallel connection. There are many sizes of batteries. Large batteries with more material can supply more current. In addition to the many sizes and shapes, batteries are classified according to their chemical makeup and if they are rechargeable or not. Primary batteries are not rechargeable and are discarded when they run down because the chemical reactions are reversible. Then secondary batteries are reusable because the chemical reactions are reversible. The following are some important types of batteries. Okay, battery types. Alkaline MNO. This is a primary battery that is commonly used in palm-type computers, photographic equipment, toys, radios, and recorders. It has a longer shelf life and a higher power density than a carbon zinc battery. Carbon zinc battery. This is a primary multi-use battery for flashlights and small appliances. It is available in variety sizes such as AA, C and D. Lead acid. This is a secondary rechargeable battery that is commonly used in automotive, marine and other similar applications. Lithium ion. This is a secondary battery that is commonly used in all types of portable electronics. This type of battery is increasingly being used in defense, aerospace and automotive applications. Lithium MNO. This is a primary battery that is commonly used in photographic and electronic equipment, smoke alarms, personal organisers, memory backup, and communication equipment. Nickel metal hybrid. This is a secondary rechargeable battery that is commonly used in portable computers, cell phones, camcorders, and other portable consumer electronics. Siloxane. This is a primary battery that is commonly used in watches, photographic equipment, hearing aids, and electronics requiring high-capacity batteries. Zinc air. This is a primary battery that is commonly used in hearing aids, medical monitoring instruments, pagers, and other frequency use applications. Hands-on tip. To store a lead-acid battery for an extended period, it should be fully charged and placed in a cool, dry location that is protected from freezing or excessive heat. A battery will self-discharge over time, so it needs to be periodically checked on, recharged with less than 70% fully charged. Battery manufacturers will have specific recommendations for storage on their websites. I have learned something about the batteries now that I should read what kind of battery it is, and yeah, and maintain them that way. For example, like the standing here. Fuel cells is a device that converts electrochemical energy into DC voltage directly. Fuel cells combine a fuel with an oxidizing agent. In the hydrogen fuel cell, hydrogen and oxygen react to form water, which is the only byproduct. The process is clean, quiet, and more efficient than burning. Fuel cells and batteries are similar in that they both use an oxidation reduction chemical reaction in which electrons are forced to travel in the external circuit. However, a battery is a closed system with all its chemicals stored inside, whereas in a fuel cell, the hydrogen and oxygen constantly flow into the cell where they combine and produce electricity. Hydrogen fuel cells are usually classified by their operating temperature and the type of electrolyte they use. Some types work well for use in stationary power generation plants. Others may be useful for small portable applications or for powering cars. For example, the type that holds the most promise for automobile application is the polymer exchange membrane fuel cell, PEMFC, which is a type of hydrogen fuel cell. A simplified diagram is shown in figure 12 to illustrate the basic operation. The channels disperse pressure the hydrogen gas and oxygen gas equally over the surface of the catalyst, which facilitates the reaction of the hydrogen and oxygen. When an H2 molecule comes in contact with the platinum catalyst on the anode side of the fuel cell, it splits into 2 H plus ions and 2 electrons. The hydrogen ions are passed through the polymer electrolyte membrane, PEM, onto the cathode. The electrons pass through the anode and into the external circuit to create current. When an O2 molecule comes in contact with the catalyst on the cathode side, it breaks apart from 2 oxygen ions. The negative charge of these ions attract 2 H plus ions through the electrolyte membrane, and together they combine with electrons from the external circuit to form a water molecule, which is passed from the cell as byproduct. In a single fuel cell, the reaction produces only about 0.7 volts. To get higher voltages, multiple fuel cells are connected in series. Current research on fuel cells is ongoing, and it's focused on developing reliable, smaller and cost-effective components for vehicles and other applications. The conversion to fuel cells also require research on how to best obtain and provide hydrogen fuel where it is needed. Potential sources for hydrogen include using solar, geothermal, or wind energy to break part of water. Hydrogen can also have time by breaking down coal and natural gas molecules, which are rich in hydrogen. Solar cells. The operation of solar cells is based on the photovoltaic effect, which is the process whereby light energy is converted directly into electrical energy. A basic solar cell consists of 2 layers of different types of semiconductor materials joined together to form a junction. When one layer is exposed to light, many electrons acquire enough energy to break away from their parent atoms and cross the junction. This process forms negative ions on one side of the junction and positive ions on the other, and thus a potential difference is developed. The figure 13 shows the construction of a basic solar cell. Although solar cells can be used in room light for powering a calculator, research is focusing more on converting sunlight to electricity. There is considerable research in increasing the efficiency of solar cells and photovoltaic PV modules today because they are a very clean source of energy using sunlight. A complete system for continuous power generally requires a battery backup to provide energy when the sun is not shining. Solar cells are well suited for remote locations where energy sources are unavailable and are used in providing power to satellites. Scientists are working to develop flexible solar cells that can be printed by a banknote printing process. The technology uses organic cells that can be mass-produced cheaply by printing them in the same manner as money is printed. Printable electronics is the foremost of polymer technology research. Here is a basic source. Top contact, transparent anti-reflective coating, semiconductor layer, junction semiconductor layer, bottom contact, voltage, top contact. Cutaway view of a DC voltage generator. Electric generators convert mechanical energy into electrical energy using a principle called electromagnetic induction. A conductor is rotated through a magnetic field and a voltage is produced across the conductor. A typical generator is pictured in figure 14. Okay. Power supplies convert the AC voltage from the wall outlet to a constant DC voltage that is available across two terminals. A basic commercial power supply is shown in figure 15. Thermocouple is a thermoelectric type of voltage source that is commonly used to sense temperature. A thermocouple is formed by the junction of two dissimilar dead metals, and its operation is based on the Seebeck effect that describes the voltage generated at the junction of the metals as a function of temperature. Standard types of thermocouples are characterized by the specified metals used. The standard thermocouples produce predictable output voltages for a range of temperatures. The most common type is K, made of chromal alumel. The other types are also designated by letters EG and BR and S. Most thermocouples are available in wire or probe form. Piezoelectric sensor. These sensors act as voltage sources and are based on the piezoelectric effect, where voltage is generated when the piezoelectric materials are mechanically deformed by an external force. Quartz and ceramic are two types of piezoelectric material. Piezoelectric sensors are used in applications such as pressure sensors, force sensors, accelerometers, microphones, ultrasonic devices, and many others. Define voltage. Voltage is the helps to produce current, and the unit of voltage is volt. What is the voltage? I think I will. have this here. Voltage is needed to produce current. Volt. Yeah. V equals seven sources of voltage. That was pretty much. Okay, det har jag. Okay, fuel cell, solar cell, generator, power supply, 1, 2, 3, 4. Thermocouple. Yes. So electric sensor. Battery. What type of chemical reaction occurs? All types of batteries use a specific type of chemical reaction. Called oxidation reduction reaction. That's about it.